please welcome Jake and Eric.
So I'm Eric Sherman, and I'm from Microsoft, and I work on Bing, where I'm a principal development lead in charge of end-user-facing performance. And I'm also on the Velocity Program Committee and was involved in putting together the conference.
I'm Jake Brutlog. I'm an analyst with Web Search Infrastructure at Google.
And it's a little bit unusual to see Microsoft and Google up on stage together doing a joint presentation. And so what happened in this case was there's really not a lot of good information out there about the business impact of performance changes to a site. And we found that both Microsoft and Google had done some experiments in this area, and we found that our results complemented each other well, and we wanted to present them together because we wanted our messages to reinforce each other. So at Microsoft, I'll be speaking about 3 classes of experiments that we ran at Microsoft. I'm first going to cover an experiment in which we introduced delays on our servers and the results that we found at Microsoft. Then I'm going to hand it over to Jake, where they ran very similar experiments, and he'll talk about what they found. Then I'm going to cover 2 additional types of experiments in which we either slowed down the page or sped up the page in a couple of different ways in what we found. So a little bit of background on experimentation. So many of the big players in the industry, Microsoft, Google, Amazon, et cetera, have experimentation platforms that let us try out features or try experiments on users and on a small fraction of our users before we deploy them to the rest of our user base. And the way that these tend to work is that we'll take all of our users and we'll divide them up into very small buckets. And then we'll be able to take one bucket and give it a control treatment, and another bucket and give it an experimental treatment, and then measure how certain metrics vary between those 2 buckets. So, for example, in search, we can look at how many searches a user is doing per session, how often they come back, what they're clicking on, what revenue is, etc. And these kinds of systems are tremendously valuable. They're way better than running usability tests, and they let you test the impact of something that you want to release on just a small fraction of people before you unleash it on your entire user base. They're highly worthwhile. So why test performance? Everyone knows that performance is important, but no one really has good data on how important it is. And you could just say that faster is always better, but that's not always the case. What if you've got a real trade-off between, say, relevance and performance, or some other feature set and performance? So the fastest page is really an empty page, but that's not going to do anything for your users. So at both Microsoft and Google, we wanted to measure how important it actually was so that we could prioritize performance work against other work, so that we could figure out what the right gates were around release criteria for performance, so that when we were releasing new versions of the site, we could hold it to certain standards. And we also wanted to have a knowledge of how much performance mattered so that when we were looking at other kinds of experiments that we were running on other features, we could tell whether the changes that we saw in a user group were because of performance or because of the other features that were being introduced. So the first experiment was to measure the impact of delays that we added on the server. So in search, we take time on the server. Generating the right results isn't trivial, and spending more time may result in a better page. So at Microsoft, we ran 5 different experiments. And in these experiments, we would receive a request, and then in each experiment, we'd add a different static delay on the server. And so that delay ranged between 50 milliseconds at the fast end all the way up to 2 seconds at the slow end. And we thought that this might have a big impact on users. So what we did was we only used very small buckets of users, very small numbers of users overall, and we tightly monitored what the impact was on users. And sure enough, at the slowest end, we had 1 and 2 second experiments. We found that there were big impacts on users that we saw very quickly, so we turned them off after a very short period of time. The rest of the experiments we ran for about 3 weeks. And what did we find? Here's a summary of our results. So the dashes mean that there were no statistically significant deltas. Any place where we do have a number that was a statistically significant change. So across our 50 millisecond delay flight, we found that there were no statistically significant changes. At all of the lengths of time above that, we did see significant deltas. So some interesting points. There were strong negative impacts across all of these metrics. Metrics ranging from repeat usage to revenue to user engagement to a heuristic that we have that tells us what the general customer satisfaction was with this experiment. And in the 2-second experiment, we saw that there were almost 2% fewer queries that we got submitted from users, fewer distinct queries. And we found that the revenue per user dropped by about 4%. And as you look down the chart in a particular metric across increasing delays, you'll see that not only does the impact on the metric get worse, it gets worse almost linearly as it takes longer. Another interesting metric is the time to first click. In this metric, what we found was, this is a useful metric for engagement. It's essentially from the time that we get the request, how long is it until the time that user clicks on a result? And what we found was that it increased a little bit worse than double the amount of delay that we added. So that means if we added 200 milliseconds, they took around, well, in this case, 500 milliseconds to additional time to click, which is kind of weird. It took significantly longer than the amount of delay that we added. So the theory behind this is that what's happening is that the user has an opportunity to get distracted. You're not keeping them engaged with the page. And some people may look at these metrics and say, oh, it only had a 1% delta or a few percent delta or slightly less than a percent delta, and think that that's not a big deal. This is a big deal. These are big changes. These are established users of our product, and we're seeing significant changes in their behavior over a pretty short period of time. And these kinds of changes are dramatic compared to many other classes of experiments that we run. So we also found that there's the potential for some cumulative changes over time, and here's the point at which I'll hand over to Jake.
All right, let me take a moment to describe the server delay experiments that we ran at Google. Basically, these experiments had 3 dimensions on which we varied them. The first was the type of delay, which I'll explain in a moment via this diagram. The second is the magnitude of the delay, i.e. 100 milliseconds, 200 milliseconds. And the third dimension was the experiment duration, the number of weeks at which we subjected users to this particular delay. So this diagram you see here sort of illustrates the sequence of steps of a search results page load. So the user-perceived total latency, end-to-end latency, begins at the start of navigation, which would correspond to a user clicking the search button on the home page or pressing enter if they've typed their search query into a browser Chrome search box. And the duration would span all the way until the point that the page is completely rendered. And this includes embedded content such as video thumbnails or maybe an embedded map, a stock chart, whatever results are relevant to the query the user has submitted. Now, the browser starts by performing a DNS lookup and establishing a TCP connection. These steps are, of course, both optional if the DNS information is cached and if the TCP connection is already cached. But after these 2 steps, the browser initiates its HTTP request for the page HTML content. And the first type of delay, the pre-header delay, basically means we pause all server processing immediately upon receipt of this HTTP request. Now, Google uses HTTP chunked encoding, and Eric will have a little bit more to say about this later. But basically, this means that the page header, which is the HTTP headers and all the visible content above the blue bar on the Google search results page, can be transmitted even while we haven't yet generated the results. And the second type of delay, the post-header delay, pauses all processing immediately after sending on this header, but before continuing to generate the results. Now, usually at Google, the ads and the search results are transmitted together. But if you look carefully at how the page is put together, it's actually the case that the ads are structurally first in the page, and in fact, they'll appear earlier in the network packet ordering. And so it's actually possible for your browser to render the ads before it renders the search results on the page. The third type of delay that we tested, the post-ads delay, what we did was we put the ads into their own separate HTTP chunk and then paused before transmitting the search results. This doesn't mean that we were actually sending the ads any earlier, but rather that we were sending the search results later than we otherwise would. Now, it's important to keep in mind that these second 2 types of delay, the post-header delay and the post-ads delay, can both be masked by a slow or unreliable network connection. And this is because the client is actually going to be downloading and the browser processing that header in parallel with the server processing. And if you think about it, a server delay, a post-header or post-as delay is essentially just emulating more processing time on the server side. So if you have a slow client and it's still in the process of downloading and processing that header, it's obviously perhaps not going to notice an additional 100 milliseconds added to the server processing time. Let's take a look at the results. So in general, we would say that all other things being equal, more usage as measured by number of searches per user per day would be a good thing for that to increase. And in this case, we actually observed that for all of our experiments, except for the 50 millisecond pre-header delay, we observe, in fact, fewer searches per user per day, which is obviously a bad thing. Now, searches here includes anything that generates a search results page. So in particular, this includes, for example, a suggested refinement, if you click on a suggested refinement at the bottom of our search results page, or even a next page for that matter. The 200 millisecond post-header and 400 millisecond post-header experiments suggest linearity in the response over this range of delays. Linearity would actually predict that for a 100 millisecond post-header experiment, which we actually did not run, that the impact would be 0.15% on daily searches per user. But in fact, for the 100 millisecond pre-header delay experiment that we actually ran, we observed a 0.20% impact on the daily searches per user. Now, the reason that the impact is larger may be the fact that users don't respond as well to a pre-header delay than they do to a post-header delay. Now, we do have a lot of other metrics we track at Google, similar to those that Eric just presented for Bing, and unfortunately, I won't be able to disclose any of those here today, but most of these other metrics did have a negative reflection for the 100 to 400 millisecond delays. For example, we have an abandonment metric which attempts to measure whether or not a user ends their search session satisfied or not. So for example, you can imagine doing a search and then go ahead and refining your search and then choosing not to click on any of the results presented. So we would probably interpret that to mean that you did not find what you were looking for and therefore you abandoned your search session. And we do see that with the 100 to 400 millisecond delays, we do see an increase in this abandonment rate. However, looking at averages over a 4 to 6 week period doesn't really give us the full story. In fact, as this chart conveys, there's clearly an impact that changes over time. Now, to look at things over time, we have to look at a subset of users, in particular, the subset of users who were part of the experiment or control group from the beginning based on a browser cookie. For this subset of users, if the experiment has been running for X weeks, i.e. 2 weeks, then we know that every search that those users have conducted during that 2-week period were subject to the delay. So if the experiments were running for 2 weeks, they've been suffering with 2 weeks of pain, if you will. Now what we see here in this plot is the daily percentage of searches per user between the experiment and control group for the 2 6-week post-header delay experiments. If there were no difference, we would expect the dashed lines, the red and black dashed lines, to be fluctuating about the 0% dotted line if there were no difference. But clearly on day 1 of the experiment, which is the point marked week 1 on the time series plot, there is already an impact. There's already been a hit in terms of the daily searches per user. And just as clear, we can see that over time, this gap is growing, evidence of a learning effect. We can quantify this by dividing the 6-week period into 2 equal halves of 3 weeks each. And these, in fact, are the numbers that you see superimposed on top of the slide. So that minus 0.22% and that minus 0.36% would be the first 6-week period. Whoops, sorry.
Oops, sorry.
Oh, my mistake. Would be the first 3-week period and the second 3-week period. And we can see that the magnitude is larger for the second 3-week period compared to the first 3-week period. And that's actually statistically significant conducted via hypothesis test. But as Eric just gave you the preview in the next slide, this still doesn't tell us the full story. So what we've done here in this slide is we've taken the time series plot from the previous slide and we've extended it into the 5-week period after we stopped injecting the server-side delays. And so right there you'll see a vertical line at week 7. That marks the point at which we stopped injecting the server-side delays. And we're continuing to track these groups of users that were in these 2 delay experiments. And we do see, at that week 7 point, we do see a significant recovery in the daily searches per user. But it does not recover fully to the control level. So once again, recovery to the control level would mean those dashed lines would be fluctuating about that horizontal dotted line at the 0% difference. And in fact, it seems obvious that even looking at the 400 millisecond delay, it's not clear that after 5 weeks that the usage has recovered to the previous expected level, to the control group level. Now, there's a couple of numbers I'll drop onto this slide as well. This is the average impact over that 5-week period for the 200 millisecond and 400 millisecond delay, average impact over that 5-week period after we stopped injecting the delay. Now, the minus 0.08% number for the 200 millisecond delay, that's actually not statistically significant. And this is because we're relying on browser cookies to identify these groups, and over time, our data fidelity degrades. Our ability to track these groups degrades. But the minus 0.21% is statistically significant, suggesting that the impact of this 400 millisecond post-header delay is persisting for a significant time after, in fact, the delay was present on the page. Now, server delays are not the same thing as adding extra bytes on the page, and Eric's going to share some results and about an experiment on that topic.
So the next experiment that we ran at Microsoft was we wanted to track what the impact was of additional bytes that we serve on the page. Many features that you add on a website are going to increase the size of the page, and we were trying to measure what the impact was. So this is different from the delays experiment, in which every user in a bucket got the same fixed delay, in that in this experiment, everybody got additional bytes, but depending on what their connection speed was, that would have a different impact on each user. So we did this by inserting incompressible HTML comments in a variety of different places on the page. And comments are much cheaper for the browser to deal with than, say, CSS or JavaScript or even HTML. So again, this is just measuring the cost of the additional bytes over the wire, not the layout costs or execution costs on the client. So we ran a lot of different experiments where we inserted this payload into the head section, each individual result, our answer section, and around some script blocks that we have at the bottom of the page. And in these experiments, we increased the size of the page overall from roughly about 5% bigger in the smallest case to about 5 times the size in the largest case. And what we found was for really small additional payload sizes, there was minimal effect. Like, we did see some statistically significant impacts, but they were small enough that it's not really worth worrying about. Weight added higher on the page had a stronger impact than weight added lower on the page. This makes sense. If something is being rendered below the fold that a user would have to scroll to see, it's probably not going to impact them as much as stuff really high up on the page. We did find an impact on page load times that was kind of what you would expect given the size of the additional content. But we ran this test only in the US. We expect that we would have seen a bigger impact on page load times in regions that had poorer connectivity. And we're planning on rerunning these experiments later in a more global way. We found that click metrics, what somebody did when they were on the page, was more impacted than how often they were to reuse the site and the kinds of queries that they submitted to us. In our largest experiment, where we increased the size of the page by about 5x, of which a lot was below the fold, but it was a big, significant increase. We found that we had a drop in usage of about 0.55% of clicks on the page, and we didn't see any changes to our query metrics. Now, these results only apply to adding bytes in the form of increasing the size of the HTML response to serve the page. This isn't talking about, say, making multiple GET requests. That we would expect to see a significantly larger impact from that because you've got round trips involved, and round trips are slow. So now let me go to the last experiment. This is actually quite interesting. This was a progressive rendering experiment. In search, some parts of the page are very quick to generate. On this chart, on this graph, everything above the red line is very fast. That's our visual header. You don't have to determine results or anything like that. It's just you can calculate it as soon as the user hits your servers. Everything below the red line is slow to compute. You've got to go off and get ads. You've got to go off and get your web results, any answers that you've got, etc. So what we want, even though the time for rendering our entire page is very fast, we're way sub-second in general, we still wanted to see what the impact was of sending down just the header when it became available, and then the results when they became available. And to do this, we used chunk transfer encoding as specified in HTTP 1.1. And the way that this works is instead of sending down a content length header that specifies the entire size of the HTML response, you send down a series of chunks, each one of which specifies its own length. And so we would send down the top part of the page in one chunk, and then the rest of the page later as it became available. And there are some complications with this. It does impose some additional design complexity on your application. It imposes some visual look and feel limitations. You'll notice nothing at the top of the page is difficult to create on the servers. If it were, we'd have some pause in doing it. It also means that things like cookies are harder, because let's say that your results might impact what cookies you want to set. Well, you've already sent your HTTP headers, so you have to set your cookies in script instead, at least for things that would be affected by stuff after that red line. And there's a couple of issues around CSS and that sort of thing. And here's what we found. This was a big deal. There was a large improvement in performance across all of our different percentiles. We found, and this is because while the user is downloading the visual header, the servers are in parallel retrieving the results. So you've got parallelization there. We found that the time to first click was much faster. This makes sense because the user has an immediate indication that the server has responded. They don't look away. An interesting one is that we found that they were more likely to interact with that heading, and they were more likely to actually refine their queries. This makes sense because they have an opportunity. That header comes down immediately. They see the search box with their text in it, and they have an opportunity, even if it's only for a fraction of a second, to parse their query and realize, ooh, I could have given a better query than what I did there. We found that clicks went up, and users were more likely to page through the results because they felt faster, and they were faster. And we found that overall users were more satisfied. Now, this 0.7% is a big delta. It's large compared with many entire full feature additions. So, to conclude.
So, speed matters is a mantra that we often hear, and there's not often a lot of hard data behind it. And I think that this presentation, we're trying to do our part to provide some of that hard data. Now, if you've done any reading in the academic literature in the field of human-computer interaction, you'll see statistics that say 100 to 200 milliseconds is something that no user can actually perceive. Well, regardless of that, we have empirical data that suggests, in fact, delays of that magnitude do have a clear impact on business metrics. We've also demonstrated that the cost of the delay increases over time and persists. This means we should all be cognizant of launching a new feature that is known to hurt performance, but whose benefits are as yet unproven.
So we also found that the number of bytes that you send is really less important than where they are and what they do. Now that said, web search is a pretty lean and mean application. Our pages are really small. You might find that a 10% increase in our page size, or even a 5 times increase in our page size, is really not that many additional bytes. In your sites, you might find that your mileage varies. We found that progressively rendering the page using chunk transfer encoding was really well worth the additional complexity that it imposed on our app. And another thing is there's some popularly held beliefs that performance is mostly about things that happen on the client. And if you're looking at overall page load times, that's true. The amount of time that it takes to get that last byte is related to how many round trips you have and all sorts of things like that. But what we saw here is that some things that were only happening on the server, the progressive rendering, the delays on the server, had really big impacts on user behavior. So what this really points out is the fact that not all kinds of performance are the same. Getting something to your user quickly is more important than exactly when they receive that last byte. And one more thing. We wouldn't have been able to get any of this if we didn't have experimentation platforms. These are really important tools that let us measure what impact changes are going to have on the sites. We really recommend that you make an investment in your own companies because we found it's well worth it in ours. So, thank you much.
Thank you.